Okay, I think that for software people like ourselves, one thing that is always a bit intimidating is hardware, right? I always look at things like this. This is a Raspberry Pi Zero, and I wonder, like, if I take one of these things out, does it still work, right? I mean, I don't know much about this, but I wanted to try a little show of hands just to find out how much you know about what I'm going to talk about. So let's try this. Who knows what a PCI device is? I think pretty much everyone had picked one in their hands at some point in time. You probably know about kernel device drivers as well, right? Yeah, everyone. What about user-space device drivers? Do you ever use user-space device drivers? Of people is better, so it feels like I'm on the right track here. VFIO. Have you heard of VFIO before? Okay, good. How about mediated devices then? Okay, good, awesome. I think we're going to have brilliant takeaways from this today. Just before I start, there's obviously a little disclaimer that says that you are. I'm not committed to releasing any of this. Alexander wants to say something.
Please hold on, we'll need to read this.
You can read it later. I'm not committed to releasing this. Please don't buy anything from my company based on this talk, or not even stock or anything like that. Good. I found a statement from actually some hardware people that said that making a PCI device is actually quite difficult. And even if you know what you're doing, it takes a lot of time and a lot of money to get it right. So if you ever try to prototype some software for some device, and you actually had to wait for your hardware team to come up with a device, that was probably a challenge, and you needed something to get you going in the meantime. And something that people normally resort to is virtualization, right? I hope you like my little collage of a guy looking at a virtual device. It was the best thing I've come up with. And the idea is that it's relatively easy to write a virtual version of a device, because you can do that in software, right? And a very common way of doing that, let me try to use this, is using an emulator like Qemu. I'm sure everyone heard of Qemu here. And in this model, you have a hardware layer on the bottom with some real hardware, so network card, CPU, memory, some NVMe SSD. Then you have the host, which is, let's say, a Linux operating system running Qemu in Userspace. And we have the virtual machine on the top, which constitutes of a guest operating system and some virtual hardware. So Qemu here is doing the virtual hardware for you, right? In this example, I'm virtualizing a VirtIO SCSI controller. So there we go. The interesting bit to note is that this VM doesn't really know the difference between this virtual device or a real device. For all purposes, the VM thinks that this is a PCI device. As a matter of fact, there has been people developing real PCI cards for VirtIO recently. So you can actually get a PCI card, put it in your machine, and your physical machine that doesn't have anything to do with virtualization will just load that same kernel driver and drive this controller. So VirtIO is just a spec for a type of device, for a protocol for this device, that makes it very virtualization friendly. So there are things about the way you talk to real devices and the way you talk to virtual devices that are very different in the sense of minimizing accesses to the device bus and things like that. So VirtIO is designed to be easy to virtualize. And there is SCSI devices, network devices. We heard earlier about VirtIO Net. There is VirtIO Block, etc. And of course, that virtual controller may have some virtual disks behind it that could be backed by some network share somewhere, or some file in that block device, or whatever it is. And by the way, if you do have questions, interrupt me, because we're going to go through lots of different things here, and it's better if we cover them as we go along. Of course, you can always ask them at the end as well. Cool. So this has worked great, and it still works great, and the whole cloud industry is based on virtualization and virtual devices, and pretty much every data center out there these days will have some sort of virtualization layer at some place. But there's a but, and I've made a fire to call a lot of attention to it. And the but is, if you never had any exposure to this and you want to go and write a device yourselves. So the first point I'm going to make is perhaps not so strong, because it is true that you're going to need some familiarity with whatever environment you're using. But in this case, you would need some familiarity with Qemu and virtualization if you were trying to write a device that actually performs well. So naturally, there are other uses for virtualization, which is not just prototyping hardware. You may actually be using this, as I said, in a cloud environment or similar. And then you need to know what you're doing in order to make something that performs OK. The second point is user space drivers, as we talked earlier. So I did ask about VFIO. VFIO is basically, we're going to cover a little bit more in a moment. VFIO is basically a kernel, a framework that allows devices to be driven by user space applications. It allows user space applications to, in a secure manner, access and interact directly with devices. And that's what the whole device pass-through technology is based on, at least on this type of hypervisor. Have you heard of when you pass through a device to a VM, you take a device and you give it the whole thing to a virtual machine? You probably heard of that if you interacted with virtualization at some point. So if you're writing a user space driver, one drawback of doing things inside a virtual machine emulator is that you're going to need a virtual machine in order to interact with that device, always. Even if you're writing a user space driver. For example, we heard about DPDK earlier. DPDK is a sort of a framework as well, but it can be considered as a user space driver for network cards, right? Amongst many other things. So you need a virtual machine and perhaps some other supporting framework, depending on what you're trying to do. But there is one last thing that was the reason that motivated this whole project, and that's what I depicted in this diagram here, which is devices from a virtual machine must be emulated by one instance of Qemu. So even though we have one host there, and you have two virtual machines, you're going to have two QEMUs. And each one of these virtual storage controllers are handled by the respective QEMU. You cannot have a model like that, where you have two virtual machines, and they're driven by a single component on the hypervisor, a single device emulator. There's an exception to that, which is something called vhost. And vhost is a protocol that allows you to offload the data path of VirtIO devices to something on the host. That's why it's called vhost. So a very popular one is vhostnet, which lets the data path of VirtIO net devices to be managed by a task in the kernel. There is vhostusernet, which is what is used to offload the data path of VirtIO net devices to a component in the user space, which is then how you hook it up with things like OVS, the PDK. There are others like vhostuser SCSI, vhostuser block, etc. So you may wonder why we want to do this. And the idea here is that if you're actually focusing on writing performant virtual devices, especially I/O devices these days, you want to minimize latency as much as you can. And when it comes to minimizing latency, you want to avoid having components of your stack going to sleep and waiting for notifications. So if you think of a modern NVMe device, like the storage SSD, what has been happening as a trend, both in projects like SPDK and later in the Linux kernel with polling strategies, is that you submit a request to that device, and you don't wait for the device to send you an interrupt saying it's done. You send a request to the device, and you just keep checking. Hey, are you done yet? Hey, are you done yet? Hey, are you done yet? Until you pick up a completion. So if you're going to do that, and you're trying to emulate fast devices to virtual machines, perhaps you want to be checking the virtual machines to see if they have work. So imagine you have 100 virtual machines. You want to be going very quickly saying, hey, do you have any work? Do you have any work? Etc. And you're essentially pulling all these virtual machines, and checking this takes nanoseconds, right? And by doing that, you're cutting down a latency that was perhaps in the order of dozens to hundreds of microseconds, down to single digits microseconds or less. And if you're taking these requests and giving it to low latency devices like NVMe, maybe you want to directly talk to those NVMe devices and ask them, hey, have you completed this request as well? So you want to be using, you want that device emulator there to be the emulator for those virtual machines and the driver for your I/O devices all together. And the reason to do that in a single process is both functional and from an efficiency angle. So you could try to do with something like this, but then you're going to have each QEMU pulling, and you're going to be burning at least one CPU for each virtual machine you have, which is too much. If you have that, you can burn a single CPU for your entire host while you're processing I/O, and you can do a heck of a lot of I/O. Earlier this year, the SPDK folks said they can do more than 10 million IOPS using one core, right? But by directly talking to the devices in a very intelligent way. So that was the motivation for this. We wanted to figure out how to emulate PCI devices outside of QEMU. And QEMU has very good reasons for not offering an official kind of direct socket between these processes to say, here's the whole PCI device. But it does have support for this VFIO framework, which is how you do device pass-through. So what we thought is, what if we can use that to actually write the whole device in software instead of actually doing a pass-through for a real device? And that's what got us going. So before I get there, I'm going to cover some very superficial, very basic aspects of driving PCI devices from kernel and user space, because there's a few things I want to make sure we're all on page as we go along. And then I'm going to get to this mediated framework that no one knew about until now. So that's good. The worst thing is if I said, you know, this is, and then everyone says yes, and I say, okay, what am I going to say? What am I going to talk about? Then I'll sit here and tell jokes. Right, so kernel-driven devices. This is something everyone is familiar with. You can imagine you have, this has no virtualization, it's just real hardware with a Linux system. You have a user application, you map some memory, you get a buffer back, which is sitting somewhere on your address space, and then you make a read call. So I'm 100% sure everyone has done that. You open a file descriptor, you allocate some memory, say read from this file descriptor into this memory. So what's happening is at some point your request is going to get to a driver. So in this example, the NVMe driver. The NVMe driver will do the following. It will pin the buffer, which means, well, your application doesn't know in the physical memory where the buffer is, right? But it potentially doesn't know that. So normally it doesn't know that. So you do this in terms of virtual addresses for your application. So your application, all of these requests got to the driver with a virtual address. So the driver will pick up the physical address where the memory is and will pin it, which means the kernel memory subsystem cannot move this around, cannot swap this, cannot do anything like that. That physical memory is reserved for that buffer. And then you tell the device, via whatever mechanism is specific to the device, and say, I want you to read this data from your storage media and put it on that buffer. When the device is done, perhaps it raises an interrupt and everything completes. Right? That's simple. Now, what about user space devices? So that's when this framework called VFIO comes in. VFIO is composed of many parts. One of the things that it does is it's able to drive PCI devices. So VFIO doesn't know anything about what a device does. It doesn't know if it's an NVMe device, if it's a network card, if it's an encryption device. It just knows that it's a PCI device. So there are things about the PCI device configuration that are completely generic and are identical for all devices. And VFIO knows how to talk to that. And it can then present an interface to user space that any application can use in order to interact with that device. Now, there's a little danger there, which is imagine your application could therefore tell the device directly, I want to read or write to any arbitrary part of the physical memory. So that obviously would be a big security issue unless you completely trust this user space application, which perhaps you don't. And that's when that little box on the bottom came to be like this thing called an I/O MMU. I don't know how many of you are familiar with that. There are different use cases for an I/O MMU. One of them is to do with this model. So this application can allocate some buffer and tell VFIO, I want to register this buffer for DMA. When it does that, then the VFIO will pin that buffer and will configure the I/O MMU, which is a piece of hardware, saying, with a little translation table, saying, hey, every time you're told to access address 1234, that's actually here. So when your application goes directly to the device and say, I want you to read something to 1234, the device genuinely go to that address, but the MMU will translate that to the respective physical address. So you can do that to restrict where that application interface can actually go in the memory. There, as I said, there are other uses for MMU. For example, if this device could only do 32-bit addresses, but you have a machine with more than 4 gigs of RAM, the device wouldn't be able to address anything in that higher memory region. So Muser are also used so that drivers can allocate memory whatever they want in the upper regions of memory, but tell the device, then configure the MMU and tell the device, hey, your region is here in the first 2 gig, for example. But then when the device tries to access that, it jumps and accesses some part of the high memory. Cool. So this model, it's what's used to do device pass-through to VMs. So let's now imagine that this user application is inside a virtual machine, and it is Qemu that's talking to VFIO. And I appreciate that the diagram is starting to get complicated. I hope you're still with me there. The idea is that Qemu would then talk to VFIO, and Qemu will also not know anything about the specific functions of this device. It just knows that the device has these types of IRQs and regions and things, everything that's PCI generic. And then it constructs a virtual device to the virtual machine that, via its address space that corresponds to what that device actually said it can do. Then the virtual machine, when it probes that device, we will eventually load an NVMe driver, and it will be able to interact with the device. So that's why we say it's a pass-through, because the VM has direct access to the whole device. And when it's touching addresses that it thinks is part of a real device, well, it is part of a real device because they're being mapped directly to device memory. So if the virtual machine allocates some memory and say, well, I want the device to read into that, this whole mapping business with MMU will guarantee the device can get to that exactly memory address. So the only caveat here is when devices raise interrupts, the interrupts actually go to the host, and the host reinjects them in the VM. So it could be that it's marginally slower, but it's usually worked really, really well. But pass-through devices have lots of limitations. Notably, you can only give one device to one VM. You cannot really slice it up very easily. And you normally cannot live migrate this virtual machine away because it's attached to a physical device that you're not going to go there in the data center and pull it out and put it somewhere else and somehow make it work. That doesn't fly. So that's where the mediated device business came in. I need to take a course on pressing these things. So this is started with NVIDIA. NVIDIA had GPU cards that they wanted to slice up and pass through to many virtual machines, which is what today is called as vGPU. So how do you do that? One way of doing is perhaps to implement something called SRAOV, where you can split up a PCI device in multiple functions, and then it's also known as a multi-function PCI device, and then you can pass through each one of these functions to different VMs. Instead, they came up with this model called MDEV, or Mediated Device, which is a framework in the kernel that has two interfaces. One of them is a bus interface that talks to VFIO, and one is a driver interface that talks to physical device drivers that understand this mediated framework. So the idea is that, by the way, I'm still using NVMe as an example, but there really isn't an NVMe MDEV driver. There was one posted to the list, but it didn't get merged. If you look up for it, you probably find it and you can see how it works. That's why I changed it, put in quotes there. The idea is that this driver can interact with the device because it knows about the device MDEV capabilities, and it can split up this device in perhaps different individual chunks. And then it can tell the MDEV framework, here's one device, and then here's another device, and there's another device. And what happens is VFIO doesn't really know that there is only one device. It thinks there are as many devices as the MDEV framework is telling it is. So now you can use this combination of a driver and this framework to lie to VFIO and say, yeah, there are 16 devices, there are 32 devices, when in reality there's only one. And everything else works the same. So we thought, okay, what if we can build on top of that idea? We need to take a course on that. Maybe we should just resort to the keyboard. And what if we can build on that idea and actually come up with a user device, which is mediated? So think that that driver doesn't really need to talk to a physical device. There's no reason for that. It could all be done in software, but you would have to write a driver for that, which perhaps is not that easy. So looking at this model, where I took out virtualization from the picture entirely, because you actually don't need a virtual machine for this to work, you can have, again, your user application interacting with VFIO that interacts with MDEV that interacts with a driver, But this driver and this device don't really need to exist. So we came up with a model where you have a driver that knows how to talk to MDEV, and you have a user space component, which we encapsulated in a library called Libmuser, Muser for Mediated Userspace. It's a little bit of an analogy to Fuse, if you know file system user space, but M for mediated. And I don't know, we like the name in the end. And we made it really, really simple for you to write devices in user space on top of this library and present it to VFIO in this way. And then you can use this to pass these devices through to virtual machines if you want to, which is our use case. But you could just use this to write your own user space drivers if you wanted to as well. So this is so easy that I'm going to attempt to write a device with you guys towards the end of this talk. And that's the part that everyone gets excited because you most likely fail. Because I haven't really practiced that much. And we just picked a simple device that we think is going to work, and we're going to try it out. So that'll be interesting. So what do you get with Muser? Right. You can clone that if you want to. It's already up. I've published it this morning. And it's quite experimental. I wouldn't use it in production anywhere. But we're really hoping that more people are going to start using this and help us and contribute to the code. It's a fully open source project. We actually have an industry partner that is really excited about this and is helping us quite a bit. But I'm not going to reveal that yet. That's going to be later. When you clone that, you're going to get a kernel module, and you're going to get the user space library. You don't have to touch any of these things. All you have to do is build it and install it. There is one little thing that you need to add, which is a small kernel patch for the IOMMU notifiers, which is that bit where VFIO talked to us about the device. And it's more of a I'm not entirely sure you need that, but the idea is that we wanted to make these applications restartable. So if the VM was already running or you already have a driver that set up this device, the device state is kept in the kernel. And if something restarts here, we want to be able to grab that information back from VFIO. So we extended those notifiers a little bit. The guys who wrote that MDEV and NVMe driver, they had to do something very similar to this. So we expect that as soon as we have some traction, these patches will be merged in the kernel. There's also some examples, and we're actually experimenting with some Python bindings. So one of my colleagues managed to write a device, I think, in 3 or 4 lines of code that actually worked in Python. And we were hoping to demo that, but I'm not going to go that far because I didn't even try that. And if we have time in the end, maybe we can have a look at it. But I'm not a big Python guy either, so that would be a problem. I'll just do it in C. But it is really, really easy. So yes?
What's the interface between the kernel module and the library?
That's a great question. That's a great question. Sorry? I will repeat the question. Yes, the question is about the interface of the kernel module and the library, the big arrow in the middle there. I haven't really put anything here specific about the interface. It's relatively simple, but that's a second part of this talk, which we will address at the KVM forum in about a month's time in France. I will mention the basics, given that you asked. The idea is that this is a very well-documented interface, and you don't need the library if you wanted to write directly against the kernel module. The way this works is there is a management stack, similar to how VFIO works, that comes in and sets the device up. So what you need to do if you actually have a physical device is unbind the driver from the device and then bind VFIO to the device. So all stacks would do that. And what they would also do is then change the permissions of the user space interface so that your application can be unprivileged and still talk to VFIO. So when you have MDEV devices, you need to also go on MDEV and create a device by giving it a new UID. So when you do that, MDEV calls into the corresponding driver saying a device has been created with this UID. So Muser.ko, and that's the first part of the answer to your question, Muser.ko will then create, when that happens, it will create a control file on dev called /dev/muser/that_UID. So you probably want to go there and change the permissions of that thing too, so that your application running Libmuser is also unprivileged. Then you open the file and you call IO control on it with a wait flag. And that IO control blocks until Muser has something for you to do. So for you to understand what it does, you need to look into the VFIO protocol. But the idea is that when some user reads or writes to those device endpoints in VFIO, those read and write calls are going to come to Muser. So you could do that. You could do IO controls to give event file descriptors, which will correspond to interrupts. You can map parts of the device, so you can call a map on the VFIO endpoints. All of those callbacks come to Muser. When they do, that IO control wait that you called returns with some data control block that says this is what that user app is trying to do. Libmuser will take care of almost all of the complicated PCI stuff for you to make your application easier. And when Libmuser is done processing that, you will call another IO control saying done. And then it goes back to wait. We are looking to extend that a little bit to allow people to write pollable drivers and things like that, so you can do more things than just block on Muser.ko. But if you fancy doing that, you can come in and help us. So a short answer to your question is it's an IO control interface with some read, write, and mmap calls there too. But the long story was the other one. Okay, so before we go into that, let me cover some very basic and very superficial concepts that you probably need to know to use this about PCI. And then let's have a look at also the very minimum Libmuser interface that you need to write a device. And that's when we can go and have some fun and try to write a device ourselves. So how many of you have seen this PCI standard header or have heard of this before? Okay, quite a few actually. Great. So you know that when your operating system is looking at the PCI bus looking for devices, you try to read that first byte there, or some words in that some bytes in that first addresses. And if that comes back a -1, it normally means that there is nothing there. But if it comes back with anything different, it means there's a device there. And you know that the first 64 bytes look exactly like this. That's a standard for all devices. The first two words, the first 2 bytes and the second 2 bytes, are the vendor ID and the device ID. The only vendor ID I know by heart is Intel's, which is 8086. It's easy to remember. Nutanix actually has a PCI vendor ID. I don't know it by heart. And then the device ID, which is something for that vendor. The other thing you probably care about is the class code. So that tells the class of the device. For example, NVMe devices have a particular 3-byte combination of class codes. And it's based on these IDs that the kernel knows which driver to load. So when the kernel is first looking for this device, if it looks at a class code or perhaps a vendor ID or device, it's a combination of this, right? For example, there are certain class codes, which is an NVMe device, and then there are device IDs and vendor IDs that are marked as those really don't work with the normal NVMe driver, so use this other one instead, if you have it installed. Otherwise, don't even bother loading a driver because we don't know how to drive this thing. So it's a combination of these things and also the subsystem ID down there that help the operating system to know what to do with the device. The other thing you need to know about is about the regions. So this big section in the middle, which is called the base address registers. There are 6 of them, and they represent what I've marked down there as the 6 generic regions that go from 0 to 5. So the register is basically an address that tells you there is this area of the device that has some function. So the generic device stuff like VFIO or even Qemu when it's passing through a device, it doesn't really know what to do with these regions. It just knows how to interact with these registers. So when you read or write to a device, there are different semantics that can be in place. For example, if you read this, it will tell you the location or the offset of that region, the actual region in the address space of the device. Then you write a magic thing to it. I think it's a bunch of 1s. And when you read it back, instead of reading a bunch of 1s, the device responds with the actual size of that region. So there are known ways of interacting with these registers, and this is what we call register semantics. What you write is not what you read. Right? There's, for example, registers that have clear semantics. So when you write a particular word with a bit set, that actually clears the value behind it. So when you read back, that comes with a 0. if the clear succeeded. So there are semantics like that. And there are memory semantics, which is what you write is exactly what you read. And this is important because when you're coding your device, you need to know what semantics you want to give to your regions, right? And if you have mappable semantics, in order to make this performant, your user application written on top of your user device, let's say written on top of Libmuser, will share memory with the application, which means the application can write to its own memory and you get to see it straight away. And if it has just read-write semantics, then whenever the application reads and writes, that traps and goes through VFIO, MDEV, Muser, into your application. So it's a much slower path, but it gives you the opportunity to intercept reads and writes so you can do more creative things with this. So all you really need to know is these IDs for the device you want to emulate, and the fact that there are 6 regions. And then depending on the device you want to write, there are different meanings for what these regions do. You probably also want to know that there are 3 interrupt types you care about. IntX, which is a legacy interrupt. There's just one pin that can be asserted. MSI, and later MSIX, and they support more things related to interrupts. You probably don't need to know much more about that. The device we're going to play with just has one interrupt, and we only care about 1 byte in 1 region. So it's very simple. Is that okay? The Libmuser interface is also very simple then. And what you care about is describing your device. So to describe your device, you want to fill in the MDEV UID for the device. So this is which UID you're going to be interacting with. And you should probably know that because your control plane created the device with MDEV. And you need to fill in the PCI info. So the PCI info has a lot of things, but what you care about is this array called RIQ count that tells you how many of each types of interrupts you have. So IntX, MSI, and MSX is 3 entries. And then the region info, which you want to set the information about that region. So there are 6 regions, as I said. And you want to tell what's the size of the region, whether it has read or map semantics, and a function callback. So the idea is when some user access that region, that callback gets called. So you can respond to the read or write access. The IDs part and the class code, right? So of course there is a lot of advanced things in there that you can customize yourself depending on the device you're writing. Let's say you're trying to write some more complicated network card, you're probably going to need to add a lot more things there. And then Libmuser has a simple function called lm_context_run, where all you need to do is pass a pointer to one of these things, and that call blocks and drives the device for you. And you get the callbacks that are specified on the region whenever that's needed. And that's all. There's, of course, more advanced calls as well. We can create a context separately and then pull on the context and things like that separately. But this is the very minimum. So with that, I can try embarrass myself and experiment with a demo. So the demo we're going to do is a GPIO device. I mentioned Raspberry Pi earlier. These days, I think everyone is quite familiar with GPIO. It's not a Raspberry Pi. I'm just mentioning GPIO in general. It's a PCI expansion card that has GPIO pins on it. So we're going to virtualize one of this, and then we're going to have a trigger mechanism to actually assert one of the pins and see if the pins show up inside the OS as being asserted, right? So I'm going to try to cause it to load that GPIO PCI IDIO 16 driver, which is, I remember what the I is for. It's not in the video, it's something else. But I'm emulating this card from Access.io, which has that vendor ID and that device ID. I wrote it down here so I remember when I'm writing. And the device, we're not going to be triggering any interrupts from this, but the device implements one RIQ, so we have to tell in the Libmuser interface that there is an IntX, so that it constructs the address space correctly for you, the PCI header correctly for you. And whenever you try to read from the driver the value of the alt0 pin, it reads the first byte of bar 2. So that's all we need to know about this. So let's try to, it's fine. Let's try to hack that up. Okay, so can everyone read that? Okay. No? Show my glasses. I need it actually. So I'm logging into a system that. Let me start like that, and let's get some different windows going here. So I have already cloned Muser because I never rely on the internet for these things. But this is the clone you can get for it. And you want to build that. In order to build the kernel module, you need the kernel headers to be installed somewhere that it knows where to go. So in this case, I just installed the default headers. Actually, this is a 5.2 11 kernel, so it's relatively new. I have already patched this kernel with that IMMU patch and installed it to save us some time. OK, and we want to install this. So far, so good. So we can see it installed the muser.ko kernel module and installed the libmuser.so, as well as a bunch of header files for us to try out. So, right, I also have pre-prepared a virtual machine I'm calling nested. And that virtual machine will basically fire up a Qemu. It has a network device with a loopback, a network device with a loopback on port 22, being redirected from the local port 2230. So I can just SSH into my 2230 and get in the VM. And one thing you need to do if you're going to be using Muser with Qemu is make sure your memory for the VM is marked as shared. So shared is when Qemu knows it's going to have to share its memory with something else, and then it allocates, it maps them with map shared. And we need that because if you want to map the memory from this virtual machine to another process, for those advanced use cases, you want to do that. And there's a nested.qcal image. So if I fire up this VM to see if everything is working, I should probably see Qemu coming up. And thank you, I guess. And if we give it a moment, I'm sure this interface will come up. Usually take a few seconds. Any network experts in the room? All right, there it is. So what I wanted to show you, I'm inside a virtual machine I called it nested, because we're already inside a virtual machine. It's like Inception. Yeah. And if you look at the PCI devices, you see that there is just some basic stuff, and it ends on 3. That's all I wanted to show you. So let's stop this nested virtual machine. That ends. OK, so the first thing I'm going to do is well, first I'm going to show you that there isn't really any VFIO or Muser or MDEV stuff installed, I think. Good. We want that module to pick up that muser.ko, and we want to load it. Let's check again. Right. So just by loading Muser, all the dependencies were brought up, and we also loaded VFIO and VFIO MDEV and the IMMU drivers, etc. So far, so good. So the other thing that happened when we loaded Muser is that this class appeared. So you just follow the path, and you're going to get to this. This is on the README file of the project, so you don't have to photograph or take a note or anything. In there, you find the create file. This is part of the MDEV interface. And what you want to do is write the UID that you want to create into this create entry. So that's what I said that your management stack will do that for you. If you have a hypervisor and you're doing vGPU, for example, it's already doing that for you. So the UID I want to create is a bunch of zeros. So let me just copy this thing here. OK. Yes? I don't believe in stupid questions. Yeah, you can. Yeah, you can pull it. You write once to an entry called remove, which will exist once the device is created. I can show that. That's completely untested territory. Yeah. So you see that dev Muser doesn't even exist. And dev VFIO contains only a control file for VFIO. Right? Oh, one of the things we can do actually is, let me just do it like that. So the last things that happened is we know that Muser got registered, right? So I'm going to echo this. Oh, That's unfortunate. My terminal is not helping me. Okay, you can't see what I'm typing, but I'm echoing those zeros greater than create. Oh, look at that. So you see that the device got created. The kernel, the MDEV called into Muser.ko and said, hey, here's a device. Right? So if we look on dev Muser, now that device is there. And if you look in dev VFIO, you see that the entry 0 appeared. This is entry 0 there corresponds to an IO-MMU group. So the idea is that you could have multiple devices behind the same IO-MMU, and they constitute a group. And then when all the devices behind the same IO-MMU are being driven by VFIO, then you can use VFIO to interact with it. It doesn't really matter right now. What I'm also going to do is drop the permissions on this thing, so these 2 entries, so we don't have to be root to interact with it. And now comes the challenging part. Let's try to write a device. So let's try to write that GPIO device. Okay. So to help me, I'm going to open the Muser header file. And, well, the first thing we're going to do is include that thing. And we're going to have a function main that calls lm context run on this GPIO info thing we're going to define here. So that's an lm dev info, GPIO info, and we have to fill this in, right? Okay. So let's look at what dev info t we have to fill. We don't really have man pages, sorry, and terminal size is also not helping me, but that's okay. Right, so the UID of the device, we already know that it's a bunch of zeros. So PVT is an entry you can pass like an opaque object, and then when you get a callbacks for a region accesses, it will give you this back. Because it's all callback driven, you need to know what is being called back on. Then we need to fill in the PCI info, right? Is that all? Yeah, that's all. You don't need anything else from here. So let's look at this PCI info. And from here, what we need to fill is the IRQ count for the int-hex. I'm going to come back here and get the actual index for int-hex in a moment, but we know there's one of them. And I also said there is one region we care about, which is bar2, right? I'm going to come back and get the details of bar2 as well in a moment. I need to find out the actual name of the index. Oh, and then we want the IDs. So the ID is easy. There is a vendor ID, which is 494F, and the device ID, which is 0DC8. Okay. That's all. We don't need a class code, really. The device would show up as unclassified, but that's fine. And for the region info, we need the size, which is, I'm going to put 256 bytes, hope that'll work. The flags, which we want it to be rewrite. I think it's called lm reg flag rewrite. And a callback. So this is the function that gets called when someone tries to access this, this particular region. So it's called GPIO fn, and it's of this type here. So we know that it's size t, and it takes. There is some abusive use of const in this thing, which you may feel free to question on GitHub. Is right. Okay. So this is what you get back when someone tries to access this region, right? And all we need to do is to fill in the first byte with either 0 or 1, depending on what we want the response to be. And then we probably, as all read functions or write functions, probably want to return the whatever they actually thought they were reading. So as a trigger mechanism, I'll propose we have test if a file exists. So if the file exists, let's say we return 1. Otherwise, we return 0. So let me say here, if the file does not exist, we're going to set 0. So I think I also need the header for access and the header for std for printf. Right, that should be it. First embarrassing moment. How many C mistakes did I make? Loads. I forgot to fix the name of these things. So there's something which, oh, there you go. So that's lmdev intex RQ index and lmdev bar2 region index. Okay, let's try that again. Did you get that? Right. Of course it does. So all I have to do is run this, and it will open dev muser 000 and interact with that for me, right? So now we have to fire up a virtual machine that uses this. So I have I showed you this nested VM that I started with nested.sh. I have a nested muser.sh that all it does is it adds this device to the VM. That's the only difference between these two files. So I'm going to fire up this VM. We should see when the kernel is reading the device and when the kernel is interacting with this GPIO PCI device in the guest. You should read something there. So that will give us an indication that hopefully the guest booted. Oh, there you go. Okay. So I can try to SSH to this VM. That's that network business that we have to wait on. Oh, there you go. And that's a nested one. If you do LSPCI, you see that now there's a fourth device there that wasn't there before, which has the vendor ID we configured and the device ID we configured. So that's a good sign. We didn't put a class in, so it's saying it's an unclassified device. We can actually check that the kernel driver in use is what we expected, the PCI ID IO16. And if that worked, then there should be a sysclass GPIO. There is. And what we want to do is, this is also in the README, but you want to copy the contents of this base into this export entry for this particular device. And that creates an out0 pin. And if I try to read the value of this out0 pin, you see it's 0, and you see that it actually read from my application on the other end. Right? For some reason, it reads twice. It's the amount of data it's trying to read from it. So if we go back there, and we create this on file that we told our application to test, and we read again, it reads 1. It works. And with that, we probably have a few minutes left for questions. Yes. Oh.
Thank you very much for the show.
Thanks for the show.
Questions?
Yes.
One question. For example, you have some device what you split between two virtual machines, for example. Let's say it's a GPIO device. Do you have something functionality what you can split this device? For example, this pass is control only first pin and this pass is control only second pin, and protect this functionality between different virtual machines?
Right. That's a great question. As a matter of fact, I don't have to repeat it, right? As a matter of fact, one of the people that were originally interested in this wanted to do exactly that. They didn't want to do GPU, but they wanted some fancy remote USB device thing, I think, where they wanted to connect to virtual machines. And with Qemu out of the box, there was no way to do that. So it's incredibly simpler to do it like with this. All you have to do is, well, you cannot use that LM context run interface. You need something slightly more advanced than that. Actually, you could use that, but you would have to create threads. So what you need to do is, let's imagine you use that. What you want to do is use lm context run, and on one device info, and lm context run another device info from 2 threads. So the 2 threads will block on this very simple interface. There are better ways of doing that. And then internally on your callbacks, when someone writes to one pin, you can just hook that up with the information from the other device, because your single process will have shared memory. So you can just say when someone writes to a pin, then change the contents of the other pin. So it's really easy to do that. And there were, as I said, some of the original people that talked to us about this, they said, oh, that would be really, I really want to use that because I'm doing all this testing with some devices that I need to connect them between multiple VMs. So that was a very valid use case.
Okay. Thank you. Next question.
There was someone else around here?
Yeah.
No?
Okay.
Now there's plenty of people over there.
So have you done any performance benchmarks on that?
Very interesting question. So the reason we wanted to do this because we wanted to do this for performance devices. We want to use this in a hypervisor, and we want to be able to emulate some hardware very fast. We have, and the idea is that I just showed you the basic interface with the read and write, which is very slow. The mmap interface is incredibly fast. So the idea is that the driver in the virtual machine allocates some memory that he thinks is device memory. What happens is Libmuser will call back into your application saying someone is trying to map some memory, and then you grab some memory from yourself and you respond to Libmuser saying, okay, use this. So you have a page that gets past the device, and that's actually the same page or set of pages that that exist in Muser.ko. So that it's the same page that got allocated for both processes. So whenever one process writes in it, the other process can immediately see it. So if you're having a polling mechanism, which is what we tested, our application can be just looking at its own memory. When the virtual machine writes in something, you just you immediately pick it up and you process. So latency-wise, we could pass requests through with less than a microsecond overhead. So it was very fast. That's the idea is to use this for more than just prototyping business, but there are many use cases like that.
Okay, thank you. The next question.
Have you considered, is it on?
Yes.
Have you considered using config.fs for creating and destroying your PCI devices instead of writing some values to the control file?
Which control file are you talking about? You're talking about the sys class Muser MDEV1/type/whatever/create?
I can't remember.
Right. Good question. Right.
Probably yes.
This is MDEV interface. So unfortunately, we can't change that. That's the way MDEV works. So if you were to go in the documentation for the Linux kernel and look for the mediated device doc, they will show you how to write sample device. I think they use like a serial device or something. That's just how they coded up the framework. So
fair enough.
The management stacks like libvirt, etc., will know how to talk to it.
Okay, thank you. Do you have any more questions?
I think everyone's hungry. It's
Yeah.
lunchtime.
In this case, you have to select the winner for the best question.
Can it be 2 or
One.
the gentleman that asked all of the questions then? Because because the quantity.
So here is for you, and thank you very much for your presentation.
Thank you.
Thank you.
Thanks, guys.